microwave bench VSWR measurements series on microwave engineering, lecture number 6.15. VSWR stands for voltage standing wave ratio. ISWR stands for current standing wave ratio. They are always equal to each other. Therefore, instead of mentioning VSWR or ISWR, the ratio is most of the times referred to as simply SWR. By definition, SWR is the ratio of maximum voltage to minimum voltage, or the ratio of maximum current to minimum current in the standing wave pattern over a lossless line. Notice SWR is defined with respect to a lossless line. It is relevant only in case of lossless lines. Its value ranges from 1 to infinity. It assumes 1 when the line is terminated over its characteristic impedance, that is, when the line is matched load as its termination, then SWR over the line becomes 1. SWR assumes huge values when the termination is either a short circuit or open circuit, or when it is a pure reactance. For other loads, SWR value is in between 1 and infinity. SWR can be measured with microwave bench. In the measurement process with the microwave bench, first VSWR, a standing wave has to be established over the slotted section of the bench. It is established by connecting a mismatched load to the bench. Depending upon the amount of mismatch, standing wave pattern with certain value of VSWR comes into being. Then it is measured. For the sake of convenience, for the measurement, VSWR or SWR is divided into two ranges, 1 to 10 and 10 to infinity. 1 to 10 is called low VSWR range, 10 to infinity is called high VSWR range. For low VSWR range, one method is designed. It is low VSWR method. To make measurements for VSWR falling in high VSWR range, another method is devised. It is called double minimum method. In the present session, both the methods are introduced, described, and explained. Now let us move further into the course session. We start the session with a few introductory points or statements. Standing wave ratio. SWR is an important parameter giving an indication regarding the amount of mismatch between a lossless line and its load. Its value ranges from 1 to infinity. For measurement purpose with bench, total range is divided into two: low VSWR, high VSWR. Low VSWR range is 1 to 10, high VSWR range is 10 to infinity. This division is only for the purpose of measurement of VSWR with bench. Otherwise, it has no significance. Two different methods are devised to measure VSWRs that fall in these ranges. One method to measure low VSWR, another method to measure high VSWR. Now we move to low VSWR method. As already mentioned, this method is used to measure VSWR when its value is less than 10. The bench setup used for this method is illustrated here. Starting point is a source along with its source supply. If the source is a reflex klystron, source supply is reflex klystron supply. If the source is gun oscillator, source supply becomes gun supply. Source is always followed by isolator, followed by flap attenuator. Output of attenuator is given to standing wave detector, which is terminated with horn antenna. Horn antenna is supposed to give a VSWR which is in between 1 and 2. It is less than 10, so we can use low VSWR method. Now the tunable probe output is connected to VSWR. This is the setup, bench setup. The bench is terminated with the DUT, usually a horn antenna, for which SWR is to be determined, resulting in the formation of standing waves in the slotted section. Notice this is the line slotted section. It must be having certain characteristic impedance Z0. As slotted section is a lossless line, Z0 is a pure real quantity. Okay. It is terminated over horn antenna. Input impedance of horn antenna is usually different from Z0. Let us suppose it is ZL. ZL is Z0. Therefore, reflection happens, resulting in standing wave pattern. The ratio of Vmax to Vminimum in the standing wave pattern is VSWR, which we want to find out right now. The output of the tunable probe is connected to VSWR meter. Now place the probe over a maximum and using the gain varying knobs provided over the front panel of VSWR meter, move the pointer to 1 over the scale. Place the probe over a maximum. Output of the probe is connected to VSWR meter. So when probe is over maximum, there exists certain amount of deflection in the pointer over the front panel of the VSWR meter. Now vary the gain. Gain knobs are provided over the front panel. Vary the gain of the VSWR meter and see that this pointer is over 1. 1 is rightmost point over the topmost scale. Then move the probe to minimum and note down the indication of the pointer over the top scale 1 infinity, which gives the VSWR over the bench. Next, what you need to do is move it to a minimum. Let us say left side 1, or you can move it to right side 1 also, it doesn't matter. Move the probe and see that the probe is standing exactly over a minimum. When probe is over minimum, naturally the deflection of the pointer, it decreases. The pointer moves to lower deflection position. Like, let us say like this. Against the pointer, there exists certain reading over the scale. You read out, that is VSWR. Here you are using the scale 1 infinity, topmost scale, in getting VSWR, in measuring VSWR. If the VSWR happens to be within 1 and 1.3, then set the knob over the front panel of VSWR meter to expand position and use 1 to 1.3 scale to get the accurate VSWR value. Notice for the topmost scale, 1 to infinity scale, the scale is heavily congested. It is difficult to get exact VSWR value because of this congestion. To eliminate the inaccuracy that results out of this congestion, what we have to do is, when VSWR is in between 1 and 1.3, then set the knob over the front panel of VSWR meter to expand and use 1.3 scale to get the accurate VSWR value. In the case of pointer dropping to no or small deflection position, indicating a value of more than 3 over 1 infinity scale, while probe is being moved to minimum, increase the gain of the meter by 10 dB. Then move the probe to minimum and note down the indication of the pointer on the scale 310, which gives the required VSWR of the standing wave. Here the basic features of low VSWR measurement method are described. Starting point is probe is over maximum, pointer is over 1. Then move the probe over to a minimum. Now the pointer moves leftwards or in anti-clockwise direction. The reading the pointer gives is VSWR. Basic step or fundamental step. If this VSWR happens to be in between 1 and 1.3, then to get accurate, exact value of VSWR, we use expand scale. How place the probe over minimum. Pointer is in between 1 to 1.3 over the top scale. Switch knob to expand. One knob will be there. This knob you can move from normal to expand. Now use expand scale to read VSWR exactly. This is second step. Third step, it comes from first step. Second step also comes from first step. In the first step, while you are moving the probe to minimum, when the probe is on the way to minimum, pointer may fall to no deflection position. It may be somewhere here. You have not yet reached minimum. You are in between maximum and minimum. The pointer, no deflection. Then what to do? Increase the gain by 10 dB. When you increase the gain, the pointer may acquire some deflection like this. Let us say something like this. Then move the probe to minimum. When you move the probe to minimum, the pointer may be have a position like this. Whatever is the reading against the pointer over the scale 3 to 10, we have to use 3 to 10 scale. Not 1 to infinity scale, not 1 to 1.3 scale, but 3 to 10 scale to measure VSWR. Even after increasing the gain by 10 dB, there is a possibility for the pointer remaining with no or small deflection position while the probe is being moved to minimum. It implies SWR over the line is 10 or more than 10, and in such case, this method is of no use. And necessarily one has to go to another method called double minimum method. Now we have moved to double minimum method. This method is not as simple as a low VSWR method. It is used when SWR is more than 10 or 20 dB. As the low VSWR method cannot be used for such high values of VSWR. A certain minimum amount of SWR equal to 1.414 or 3 dB is required for the line so that double minimum method can be used. Notice small VSWR method or low VSWR method. It is suitable only when SWR over the line is in between 1 and 10. There is a range of validity of the method, suitability of the method. Similarly, there is a range for the validity or suitability of double minimum method. Minimum SWR should be 1.414 or 3 dB. Maximum can be anything. So range is 1.414 to infinity for this method. It can be concluded that maximum VSWR that can be measured with low VSWR method is 10 and minimum VSWR that is required for using double minimum method is 1.414. This is the setup, bench setup used for double minimum method. Source supply. Source can be reflex klystron or gun oscillator. Source is always followed by isolator and attenuator. Then standing wave detector. The tunable probe output, it is connected given to VSWR meter. Standing wave detector is terminated with slide screw tuner matched termination combination. What is this slide screw tuner? Consider a line. It is terminated over its characteristic impedance Z0, Z0. Then no reflected wave, no standing wave pattern. Therefore, SWR is 1. Let us suppose I want to establish a standing wave pattern for one reason or other reason. I want to have a standing wave pattern over this line with a considerable SWR. Let us say 5 or 10, 6, 7, anything. Then what to do? Insert certain impedance in between line and load, somewhere here. Insert. Now the line sees an impedance which is different from Z0. Because of insertion, load impedance is no more, terminating impedance is no more Z0. Hence, reflections happen, standing wave pattern comes into being. The amount of reflected wave, of course, depends upon how different is the combination, inserted impedance Z0 combination from Z0. How much it is, the combination is different from Z0. It decides the amount of reflected wave. Slide screw tuner is one which plays the role of the inserted impedance in the present description. This is the line This is characteristic impedance, match termination. If the slide screw tuner is not there, no reflected wave, no standing wave pattern. Slide screw tuner, when it is inserted, it provides certain amount of impedance or admittance in between the line and match termination. Now, the termination slide screw tuner combination ineffective gives rise to certain impedance which is different from Z0. Net result is standing wave pattern with a standing wave ratio over the line. One more point that is required to be told here is slide screw tuner is an arrangement in which there is a provision by which you can insert variable amounts of impedance or admittance between match termination and the line. Now, to use this method, a VSWR more than 1.414, let us say about 10 is to be established. And it is done with the help of matched terminated slide screw tuner as load over the bench. The tunable probe is placed over a maximum of the standing wave pattern, and by varying the gain, the pointer of VSWR meter is moved to over 1. Now the probe is moved to a minimum, and the position and depth of the slide screw tuner probe is varied until the pointer in the VSWR meter is moved to infinity of the top scale. Then increase the gain of the meter by 10 dB, and if the pointer is still over infinity or 10 of the scale just below, then SWR over the line is 10 or more. Here, certain points are given, certain description is given. If we follow this description, then a standing wave pattern gets established in the slotted section with SWR 10 or more. If the pointer stays over in between two extreme positions of the scale, even after increasing the gain, then the setting of the slide screw tuner should be changed in such an amount and in such a direction that the pointer is moved to infinity. Now, the VSWR over the line is 10 or more, and if it is fit, and it is fit to use for double minimum method to measure SWR accurately. This method requires the distance between double minimum points and guide wave. So what he is telling in the last 5 points is method requires certain preparation. Double minimum method requires certain preparation. What is that preparation? First, one has to establish over the line an SWR which is 10 or more. If it is less than 10, we can use low VSWR method. But SWR is more than 10. That's why we are coming to this method. To illustrate this method, so first what I have to do is, I have to go to a line over which there is a standing wave pattern for which SWR is more than 10. That line we have to create, we have to establish before going to illustrate the double minimum method. So what he is telling is how to establish more than 10 SWR over the line. This is the line, this is the load, matched load, this is slide screw tuner. Because of slide screw tuner insertion of impedance, standing wave pattern, place the probe over a maximum, connect it to VSWR meter. When the probe is over maximum, see that the pointer is over 1. Now move it towards minimum. While moving, if the deflection falls to 0 in the VSWR meter, then fine. It means, it implies that VSWR of the standing wave is more than 10. Sometimes it doesn't fall. You are moving towards minimum. The pointer, even when you are over a minimum, the pointer may be somewhere here, just by the side of 1, showing maybe 1.2 or 1.3. Then what to do? We want SWR more than 10, 10 or more. So to establish 10, what you have to do is certain adjustments you have to do in slide screw tuner. There is a probe in the slide screw tuner. You can move it vertically, you can move it horizontally. That provision, that arrangement is there. So by moving the way it is necessary, see that somehow the deflection falls to no deflection position in the VSWR meter while you are traveling or while your probe is over minimum. In such case, SWR over the line is more than 10. Now it is fit to use for double minimum method. Double minimum method requires two pieces of information. One is the distance between double minimum points, another is guide wavelength. What are double minimum points? This is standing wave pattern. This is minimum point. This minimum point has certain amount of power. As you move either leftwards or rightwards, the power in the wave increases. Voltage increases, therefore power also increases. You can find 2 points. One point on left side, another point on right side, where power is double the power at minimum point. These 2 points are called double minimum points. The distance between these 2 points, it is required for measuring SWR with the double minimum method. In addition to this, guide wavelength is also required. What is guide wavelength? It is double the distance between two consecutive minimum points. This piece of information is also required. By using bench, we find both these quantities for use to determine SWR. Here, double minimum method is illustrated. Double minimum points are being shown here. This is standing wave pattern. A particular minimum is selected. Here power may be certain amount. As you move either leftwards or downwards, voltage in the wave, it is increasing. Both sides, or field intensity in the wave is increasing. But power is proportional to voltage square or field intensity square. As intensity is increasing, voltage is increasing, power also naturally increases at certain points. These 2 points are identified in the diagram. At these points, let us suppose power is double the power at minimum point. 2P. Voltage or field intensity will be root 2 E minimum, where E minimum is field intensity at minimum point. The distance between these 2 points, as already mentioned, these are minimum, double minimum points. The distance between them is required. Once this distance is known, and also once the distance between two consecutive minima is known, multiplying this distance gives guide wavelength. With the guide wavelength and a distance minimum between double minimum points, one can find out SWR using this formula lambda g by pi d1 d2 distance. Procedure is move the tunable probe over to a minimum and by varying the gain, place the pointer on 3 in the dB scale of the VSWR meter. Next, move the probe to either side until pointer moves to 0 in the dB scale. So dB scale is like this, 0 here, 3 will be somewhere here, 3 dB. Now place the probe over a minimum and by varying the gain, see that the pointer is over 3. Next, move the probe to either side until the pointer moves to 0 over the dB scale. Take down the position of the probe over the vernier scale and let it be D1. Now move the probe in the opposite direction until the pointer again stands over 0 after passing over 3 in the dB scale. Note down the position of the probe and let it be D2. These two positions, D1 and D2, are called double minimum points. To measure the guide wavelength, replace the termination with a short and measure the distance between two consecutive minima. Twice this distance gives guide wavelength lambda. Once lambda g is known and the distance between D1 and D2 is also known, VSWR can be determined using this formula. Precautions: both the source and attenuator should remain undisturbed so that the wave is at the same power level and frequency in the standing wave detector until experiment is completed. For better accuracy, distances between several successive minima may be noted and their average be considered to calculate guide wavelength. These are some of the points I want to share with you for right now. To recap, an introduction to SWR is given and two methods of its measurement with bench: low VSWR method and double minimum method. Both are described in detail, elaborately. Hope you have enjoyed the session. Hope you have a transformative learning experience. Enough for now. See you soon in another session very soon. again. Bye bye.